It's a very similar to strip mining in concept, and Gedae will automatically do it for me. As it turns out, these two don't need to be subscheduled, so I can set their divider to 1. Now, what it's actually doing is these boxes, which are displayed here now, we're all running 128 vectors at a time. And by setting the divider to 128 on that, Gedae will now implement the application to only process 1 at a time. That's what we call subscheduling. If it's vectors, then that's also called strip mining. If we create subarrays in a matrix, then we apply the same subscheduling to stream the submatrices through for processing. Okay, so now that we've got that done, now we can run the application, and we'll go back to our shell so that we can actually see that it is running. And now the way that the timing is set up here is that if I terminate this application, then it prints out the average timing. And so you can see that we're averaging here a measured gigaflop rating of 0.3 gigaflops. So that's what we're able to achieve on the PPE. So what we're going to do is to look and see what kind of performance improvement that we can get by going to the SPEs on the cell processor. So the first thing I'm going to do is bring up the group control. And in the group control, I'm going to hit Run on Target Processor. And in the partition table, which I was already in for doing the subscheduling, I'm now going to define how I want the data to be partitioned. And so here I'm going to use symbolic expressions to put these in a named partition, just an ASCII string. But I can use the $1, which is this index here, 0 to 3, in order to create the partition name. So now I've created a 3 or 4 more sets, P0, P1, P2, and P3. I can do the rest of these the same way with a cut and paste. And so I've now got those all partitioned. Now the question is, where do I want to put this this box that concatenates the data back into the full matrix, and the one that partitions it? And I'm going to put both of those on P0. And then these other boxes that I already had in the graph, I'm going to open those because I actually have to put this box on P0, and that's getting me a pointer to the data in system memory from the PPE. And I need to put a box down here in the sink, and so I need to put this MZU no-op, and I also have to put this box, which is sending a flag back to the PPE for timing purposes. I need to put that into P0 as well. But what you've seen here is me partition the functionality into a set of all functional components in the system to a partitioning of that functional component. And now each of the partitions can be mapped to a processor. And in this case, they're going to be mapped to SPEs. So I'm going to go into the mapping table, and now that you can see my partitions are listed here, and I'm going to set those equal to 100 plus $1. And you'll see that when I do that, I am mapping them to these processors called the SPUs. And so those are the SPUs on the cell processor. I'm only using 4 of them here because I'm running on the PlayStation. It also turns out that I need to set up the heap size because I'm on this processor going to be allocating data in system memory. So what I need to do is set up the heap size in system memory for this processor. And I can select this and go to the view settable parameters, and here I see that I can use -H and -LPH to set up the heap sizes. So I'm going to, for this processor, which is where I'm parting and concatenating the data, I'm going to put a -H, 12, million, and then a minus LPH 12 million, just to make sure that I have sufficient room for those.
That didn't work right.
I need 2 more zeros. Okay, so we got 12 million on both of these. And now I'm going to save these group settings. And so turns out that I'm going to save them in mapped. And now I can try and run this. I might want to check the size of the data sets. And so in order to best check the size of the data sets, I'll bring up the debugger. And this is going to show me the this memory map. This map right here is going to show me the amount of memory that's being used on each of the processors. And this one's 9,400 in data elements, because this is the entire memory map. Very detailed information about it, but it's 9,400, and it turns out that that's something like 30 kbytes of data. So it's plenty small enough to fit in my 256 kbytes. And the rest are all going to be smaller than this. And so this is 7,800 versus 9,400 hexadecimal. And so they're all okay. And so it looks pretty good, so I can try and run this. And I'll hit the run button. And when I hit the run button, I'll go back to this window and we'll see that it's actually running. Once again, I don't have to wait very long. I can terminate the graph. And we again get a report, and now we're running at 1.6 gigaflops. So we went from 0.3 to 1.6, so that's about 4.8, about 5 times, wait a minute, about 50 times faster than...
Like 5. 5. Yeah.
What's that?
5 is better.
Yeah, that's about 5 times faster. What's really curious here, as a side note, is that I ran this morning, and it was running at 0.04 on the PPE. How it got to 0.3 is beyond me.
Oh.
Really strange. It was running so much faster this time than it was before.
Okay.
But on the SPE, it's running 1.6. And so now, I just show you one example of the optimizations that you can do. And I've turned on the trace, and I'm going to hit the run button again. And so now I'm collecting trace information. I'll stop the graph, and I'll bring up the trace table, and we can look at the trace that's collected. And what we'll see down here at the end is that I've got really nice parallelization on P1 through P3, but P0 is actually running serial with this other processing. And my belief, the reason for this is that I've got a scheduling order that could be better improved. And what I really want to do is make sure that I'm sending messages to free things up as early as possible. So I'm going back to the group control, and I'll show you that I can actually change the way that it's ordered that things are happening by setting the priorities. And the one that I want, and notice these are all the boxes, lots of places here to do things. So you need to do a bit of analysis to figure this out, and we'll learn more about that later in the week. But what I'm going to do is set these to a high priority, so these send requirement is happening as early as possible. And that will allow the data or the processing to progress more quickly. So I'm going to turn off the trace collection and run the graph again. And again, I'm just going to wait for it to start running. And I don't need to wait long because there are so many events that are being collected. So I'll stop it. I'm sorry. I want to terminate so I can see what the actual timing is. And you notice that I did get the parallelization, so I went from a case where those two operations are serial to now where they're in parallel, and I doubled the throughput effectively by doing that. So I want to do 2 more things, and I'm going to do both of those at once and kind of shortcut things a bit for right now. And like I said, we'll learn